So here is a 3x3 system, and we're going to just solve this one in general. Yes, so our first task would be to find the eigenvalues. So in order to find the eigenvalues, we would subtract lambda from the main diagonal. So we got negative lambdas there everywhere and ones everywhere else. And so that gives us, if I expanded about, let's say, the first row or column, actually we get the same thing if we do that. So negative lambda times lambda squared minus 1 times negative lambda minus 1, and then plus 1 times 1 plus lambda. And simplifying all of this, right, equal to 0, that simplifies if you do the math on that. Negative lambda cubed, that's from this times this. Sorry, this is going kind of crazy here. I'll stop doing that. Then plus 3 lambda, let me see, that would be plus lambda here, plus lambda here, plus lambda here, so 3 lambda, plus 2, and notice there's no lambda squared term because they just aren't there. So how would you solve an equation like this? So we're using the rational root theorem. Only possible roots are plus or minus 1 and plus or minus 2. And noting 2 is a root because, you know, negative 2 cubed plus 3 times 2 plus 2 works. So we could factor this, and if we do, we also have a double root of negative 1. So we got lambda equals 2 and lambda equals negative 1 is a double root. First, let's do the negative 2. If we want to solve this equation to find an eigenvector associated with that, here's the augmented matrix. Switch rows 1 and 3. Kind of makes nice to have a 1 here in the upper left. And then negative row 1 add to row 2 will make a 0 here. And 2 row 1 add to row 3 will make a 0 there. And then we'll get this result. That would be our augmented matrix. Then we want to do negative 1/3 row 2 and then negative 3 row 2 add to row 3. And that will give us this configuration. By the way, the negative 1/3, that would make this a 1, not a negative 1. And then negative 3 times that, negative 3 times that 1 added to this makes a 0. And if that's a 1, negative 3 times that add to that, oh, that would be a negative 1 actually. That makes that a 0. So we got a row of zeros at the bottom. So it looks like with the K3 arbitrary, we get K1. By the way, this second row says K2 minus K3 equals 0, so K2 equals K3. The top row says K1 minus K3 equals 0, so K1 equals K3. And we've got our eigenvector 1, 1, 1. That's associated with eigenvalue lambda equals 2. But for lambda equals negative 1, go back to original, if lambda is negative 1, here it is, then we got 1s everywhere. And we want to find a solution for this system. Here's the augmented matrix, and row operations negative R1 plus row 2 and negative row 1 plus row 3 gives us, except for the top row, all zeros. So K3 and K2 are both going to be arbitrary, and K1 equals negative K2 plus minus K3. And so, if that's what K1 is, we have this vector as the eigenvector, but look, that's two different vectors. That's constant K2 times negative 1, 1, 0, plus constant K3, negative 1, 0, 1. So that's really two different vectors, and so we've got two linearly independent vectors with our one eigenvalue of negative 1. So here's the general solution. C1 times the eigenvector we found associated with 2 plus C2 times one of the eigenvectors we have found associated with lambda equals negative 1 times e to the negative 1t plus C3 times the other eigenvector we found associated with lambda equal negative 1 times e to the negative 1t. And that's our solution.
Oh, I see.
Okay.